Hello and welcome back to Calculus 1 on this wonderful Saturday morning. We are going to take a look at exam 2 review, since you picked to have one next week. We are looking into standard stuff, right? Chapter 3, about 10 problems. Exam is 1 hour, 20 minutes. You know, we can go 25 minutes or so. But there's a standard class time. Your quizzes start tomorrow, which is 3:31 at 6 a.m. and there will be 7 of those. They're open 18 hours a day. We say unlimited amount of tries, but it's, what do you get? 36 tries at most, right? I guess. And what is on the test? Well, it's chapter 3, so derivatives. And the list goes like this. So we have the limit, definition of derivative. Now this is taking the derivative using the limit h goes to 0 of f of x plus h minus f of x divided by h. So this is our, right? And then number 2, basic derivative formulas. So to avoid working on this limit every time when we need to take the derivative, we memorize those shortcut formulas and then the rest of the chapter unfolds. So what is the first one? It's a basic derivative formula. We have constant x to the n. Then we have all the trig ones. We have e to the, let's say, f of x. We have ln f of x. We have, what else is there in basic? I don't know, I'll add if I remember. Number 3, product plus quotient. Then we have inverse trig over here. Inverse trig. Then product and quotient. Then we have chain rule. Number 5, implicit. Number 6, logarithmic differentiation. And then we have 2 sections that are word problems, and those are related rates. This is where we did all those speed and velocity and acceleration, and then we did business application. And then 8, related rates is 8. Not related. That was the last section we just did. The rates of change. Rates of change is where we did all the velocity, speed, acceleration, and business application, population change. Let me put that. So velocity, acceleration, population, business, right? And then related rates was taking the derivative in respect to time, right? Which was all of the geometry and stuff we had. And there was that one section that was graphing the derivative, looking at the basic function. That was, I think, the second lecture we have. So number 9, graph or sketch dy dx looking at basic f of x. So this is the entire exam. So you are looking at a one limit problem to do the long way. I will suggest you practice this stuff using 2.3 because that's the skill that we are using. So for instance, use the limit definition to find the derivative of y equals, let's say, 5 over x. So that's a standard question, right? And then you just go and say, all right, f of x is equal to 5 over x. F of x plus h, because I need that for the formula, is 5 over x plus h. And then you go and you say, okay, the derivative is limit h goes to 0 of 5 over x plus h minus 5 over x divided by h, and then you just work the algebra. Limit h goes to 0. We add fractions on top. So you have 5x minus 5x minus 5h divided by x times x plus h, right, for the common denominator. Then you have to keep copying this limit all the way to the last step. 5x's drop. So now you have negative 5h and then the 2 that are close by, because you can put h over 1 over here. It's a double fraction. So 1 multiplies negative 5h, and in denominator you have x, h, x plus h, and now h drops, and you have the limit h goes to 0 of negative 5 over x times x plus h. Now if h goes to 0, then you are left with negative 5 over x times x, and that's just negative 5 over x squared. Now the cool thing about these problems doing a long way is that you can check, because you know the shortcut method, right? You can check the validity of your answer from the problem that is 10 points by taking the basic derivative, just saying, okay, d dx of 5 over x, right? And then you go and say, all right, so this is the derivative of 5x to the minus 1. And you remember that you can kick the constant in front of the derivative. That was one of the properties. So you just have to take the derivative of x to the minus 1. So this is 5 times, and now for x to the minus 1, you know, you drop down the exponent, and x to the minus 2. And that becomes 5x to the minus 2, which is minus 5 over x squared, and that's the same, right? So there is a way for you to check these problems and make sure you did them correctly over there. So that takes care of that part. And now the rest is figuring out, do you have a product rule, you have a quotient rule, you have chain rule, do you have implicit differentiation, logarithmic differentiation. I did talk about all of these, right? You have the videos and notes and everything. So I forgot to write the most important thing, which I always write in red on the list, and I was about to say it now and just hit me like a truck. Holy nightmare. In red, in blood. Number 10, tangent line problems. Wow. So tangent line problems. That is very important, because I did tell you that you guys will have tangent line problems on every single exam, exam 2, exam 3, and the final exam, and then they're gonna grow into, change name and grow into something else when you go later on the... No, I don't want that. Undo. I'll figure out. So, for tangent line problem, we can have any derivative. Any derivative technique. So the procedure for tangent line is number one, well, let's go. Take the derivative. Of f of x. Number two, slope is the derivative calculated at the point. Number three, use y equal f of x to get y, because y is not always given to you. Number four, use y equal mx plus b to get b, because you have the rest, right? The x is given to you. You calculate y if it's not given to you, and you calculated m using the derivative. So you calculated 3 out of 4, you just need b. And then number 5, win, which means you just write the tangent line. The simplest example is find tangent line at x equals 3 for y equals x squared. Now, you can't have cheaper problem than this, right? You just go down the list. F prime of x is 2x. Slope m is f prime computed at 3, so that's 2 times 3 is 6. Y equals, so now I don't have y yet, so y is f of x, I mean f of 3 in this case, so that's 3 squared is 9. So I have x, I have y, I have m. So y equal mx plus b, x is 3, y is 9, m is 6. Plug in. Y is 9, m is 6, x is 3, plus b, so b is negative 9. And win, right? 6x minus 9. Now, this is the cheapest possible problem for tangent line that you can possibly see across the board. And what is the rest? Where's the rest of the problems that are harder? Just what type of derivative you're taking. Product rule, quotient rule, chain rule, implicit. So derivative is the only thing that changes. you're looking at the procedure that is standard procedure. The only thing that is different problem to problem is the way to find the derivative, which is the entire section, right? Different ways to find different derivative of different types of functions that are products, quotients, composite functions for chain rule, and so on. The word problems we covered in our last two classes. At least two word problems, right? At least two. One on one word problem from each section. Generally, it's a velocity problem, and then one of the geometry problems. Geometry problems are either triangle or rectangle or cone or cylinder, or what else is there that it's, or a ball like a sphere. And we had the entire lecture on how to memorize easily the volume of, I'm going to scroll to it now, how to memorize the volume formulas for all of them. You'll find that in notes and the video lecture. So capital B in this case is the area of the base on which the object stands. So for our soda can that I started today with earlier, soda can has a circle on the bottom, so that's pi r squared. So if you want to calculate the volume of the soda can, pi r squared times the height of the soda can. If you want to calculate the volume of this room, your base on which the object stands, which is capital B, the area is length times width, because this is a rectangle, and then times the height of the classroom, in this case 10 feet, right? So you get the volume of that. And then in the middle, you have what I call spiky objects, right? They also have the same base, which is a square, rectangle, circle, triangle, right? So you can always find the area of that. It's just 1/3 times, and then times the height. So the only one that you actually have to work hard on memorizing is the formula for equation of the sphere. And you guys will have that one explained and proven in Calc 3 when you do spherical coordinates for triple integration in 3D, obviously. You will be proving this formula in literally 2 lines using the triple integration spherical coordinates. Right now, this is a formula, memorize it. Now, obviously, ancient Greeks came up with this formula without calculus, about 2,000 to 1,500 years before calculus. Or no, 2,000 years before calculus. Yeah, they knew this formula. But today, with the calculus tools, it's very simple for us to prove and show this formula. So these are the volume formulas, and then you have your Pythagorean theorem. You have your for the triangle, and we did quite a few of those problems along the way. So other problems are clearly derivative of implicit differentiation, which is important for related rates. So derivative in respect to time of xy squared minus cosine y is equal to 9, right? Stuff like that. So this could be also for a tangent line, right? So you have to take the derivative of it. And if the formula is showing up in related rates, then you're taking derivative in respect to time, not in respect to x. So anytime when the variables match, you don't have to write the chain rule, which is write dx over dx. So that's 1. Anytime when the derivative and the function don't match, like in this case x and a y, you have to put dy dx. So going back to related rates, you see anytime when I took the derivative of x or y, I had to follow by chain because they don't match, right? You were taking the derivative of x in respect to time, you have to put the chain. But if I'm taking derivative of x in respect to x, then the chain is dx dx, and that's 1, so I don't have to write it. So if I'm taking this derivative here, I recognize the product rule on the first one, because I have function x times function y squared. So copy the first, the derivative of y is 2y, and here is where the chain rule kicks in, because I took derivative of y in respect to x. Plus copy y, the derivative of x is 1, and I'm taking the derivative of x in respect to x, so I don't have to write the chain. So we can just ignore it. Minus, here is another derivative of y. So derivative of cosine is negative sine, so it's going to be plus sine y. And then again, I took the derivative of y in respect to x, so I have to write the chain. On the other side, derivative of a number is 0. So now, keep all of the terms with dx dy on the left, so 2xy dy dx plus sine y dy dx, and kick everything that doesn't have dy dx on the right, in this case just negative y squared. Factor out dy dx and divide into the right hand side, and we're done. Now, I did mention that if you have a tangent line problem involving the, did say this last time, right? Tangent line problem involving the implicit differentiation, don't go through algebra, just plug everything on the first line, because you have your x, you have your y, and each dy and dx becomes m, right? So you get to do arithmetic immediately, rather than shoveling through all the algebra and worrying about minus signs and, you know, dividing expressions and all this stuff. You just plug all of the x's and y's in the quickest equation that you possibly can. And that's it. The other issue was the logarithmic differentiation, when you have complicated derivatives that you can do in one shot. Did anyone bother to learn the ways so you can just look at the problem and know the derivative? All right, so if we are taking the derivative of, let's say, x cubed times the fourth derivative of x squared plus 1 divided by sine cubed x, or something like this, right? We said that we have to use ln. So y equals, leave some space, and then you have your x cubed, fourth derivative of x squared plus 1 divided by sine cubed x, and then you ln both sides, and then you expand. So ln y is equal to 3 ln x plus 1/4 ln of x squared plus 1 minus 3 ln sine x as the argument. And now when you differentiate in respect to x, it becomes a joke. So 1 over y dy dx is equal to 3 over x plus 1/4. You put the function down, remember, right? And its derivative on top, minus 3 times sine x, and the cosine x goes on top. Then you leave dy dx alone and move y to the other side, and y is x cubed, fourth derivative of x squared plus 1 over sine cubed x. I'm just going to use orange over here, say that's your y from that was moved from the left, right? So I'm just going to put a little star there. You can find it, y star. And the right hand side now is 3 over x plus x over 2 times x squared plus 1 minus 3 cotangent x, and that has to have that thing right there. So this is what we have for logarithmic differentiation. So logarithmic differentiation, now again, if you are able to mentally take this derivative without writing all of these steps, just don't mess it up, right? Because then there are no steps for partial credit. So you either write out the steps or you practice this so much that you know you won't make mistake by writing down the answer. So that's logarithmic differentiation. There's implicit differentiation. That's tangent line across the board with the procedure for tangent line. The limit derivatives using the formula. And, the rest is just, product rule, quotient rule, chain rule. Those formulas. You just apply those formulas and the word problems, right? We did 2 today as a warm-up. You have a whole bunch of problems done in related rates. And for the rates of change, word problems, you are looking at the velocity and speed, population change, something that you take the derivative of what you have and plug numbers in. Far less stressful than related rates, right? Where you have to figure out geometry and implicit differentiation and plug everything in. So that's easier. Any questions, concerns, problems from homework or anything that you would like me to work out? As a review. This is the best when I'm so clear and clearly like presenting the materials. It's impossible not to understand, right? And
like when you have a graph and you have to graph the derivative.
Graph the derivative. Okay, so for f of x, we draw f of x in black, and then we'll do derivative on the same xy axis but in red. So let's say you have, this is xy axis. It's a terrible arrow there, but such is life. Let's say you have something like this. And wondering what the derivative is. Well, first off, asymptote gets preserved, and every minimum point that you get is the cross on the x-axis. So this part of the function is decreasing, this part is decreasing, this part is increasing. So when you have a decreasing line, the derivative is also the derivative is below x-axis. So in this case, these two are pretty much the same thing. Now on the other side, you have a decreasing function. Derivative has to be below x-axis and following the asymptote. On the other side, it's increasing, so it's going to look like this. So red is f prime of x, and black is f of x. So the rules to sketch the graph of derivative looking at the function are: if the function is decreasing, the derivative is negative, meaning below x-axis. If the function is increasing, the derivative is above x-axis, meaning positive. Anytime you have a min or a max, you have a 0 on x-axis at that point, and all of the vertical asymptotes are preserved, which means they are the same for derivative and for the function. Good one to think about would be, let's say, tangent, derivative of tangent, right? Because tangent is, tangent has its vertical asymptotes at every pi over 2, and derivative of tangent is secant squared. Well, if you are to graph secant squared, if you don't know what it looks like, you will find very quickly that secant squared has the vertical asymptotes, exactly what tangent had. So vertical asymptotes are preserved. You have those sort of 4 rules, right? 4 rules that you have to memorize. Vertical asymptotes preserved. Every min or a max will create a 0, which means a dot on the x-axis. All of the decreasing parts of the line, the derivative is below x-axis, and all of the increasing parts of the line for that interval, the function is above x-axis. And that's that. That's the it's graphing the functions. Now these are sketch, right? This is not exactly, so I don't know how fast this is rising, or is it sluggish, is it faster? We actually have to look at something called concavity and other things that are going to be there. Now this over here looks almost linear, so it should be much flatter than what I drew, because this is pretty much a constant rise here, so it should be pretty much a constant flat, right, piece, because the rate of change is constant in that case. If you have a constant increase in a function, then you have a constant change in the derivative, meaning flat, right? No change. If something is constant, but yeah. Cool? Good smile? Yeah. That's fake smile. I'll take anything this morning. Well, you started off wrong, so. Anyway. Anything else? Questions, concerns? So, going once, like an auction. Going twice. Going sold. All right, fine. Bye.